Okay, I'm Megan. I'm going to be talking about higher dimensional gravitons, specifically Kaluza-Klein gravitons, and then what the Kaluza-Klein model led to after that. Maybe? No? Oh, okay. So yeah, Anthony talked about this a little bit last week or 2 weeks ago. So one reason why we want to look at the extra dimensions for gravitons is the hierarchy problem. So why are all the forces besides gravity, or why are the strong electromagnetic and weak force much stronger than gravity? You can see the discrepancy there. It's quite large, 10 to the 32. And then also the problem of why is the Higgs so much lighter than the Planck mass. So you see the discrepancy there. And also another reason for the Kaluza-Klein theory was the start of grand unification in a way. So grand unification wonders if all the forces are actually the same force. So instead of actually having our normal 3 symmetries that we have in the standard model, what if there's just one symmetry, like SO5, SO10, something larger than that? So far they've been able to unify the electromagnetic and the weak force together into the electroweak force. So it was thought that way back towards the beginning of the Big Bang that there was actually one force, and when it cooled down there was spontaneous symmetry breaking, which gave the W and the Z their mass and kept the photon massless. So right now they're working on including the strong force, but there hasn't been much including gravity in this unification. So Kaluza and Klein, these were actually 2 separate physicists at the time that happened to work on similar things without knowing at first. So in the original idea, so this was before the strong and the weak forces were even discovered, is they wanted to unify electromagnetism and gravity. So in 1919, Kaluza thought, what if we introduce a 4th spatial dimension, and all the fields will be independent of this 4th spatial dimension besides gravity. So only gravity can propagate to this 5th dimension. In 1926, Oscar Klein thought, what if this extra dimension was compactified? So he thought this 5th dimension would be a circle of a very small length, and that this circle would obviously be periodic. So you would keep going, whatever the particle is, would keep going around in the circle. So what is curved space? Why are we even having a curved extra dimension that's so small? So this is where they kind of got the idea from Einstein, where if you have curved space-time, what if a physical dimension is actually curved? And also, how could we not notice this extra dimension? Well, one idea is if it is a circle, if you think about seeing a cylinder that has a radius so small it just looks like a line. So we wouldn't see it because it would be so tiny, but it would actually exist. So this is just kind of a sketch drawing of maybe this is our 3D plane, and then this is the extra 4th spatial dimension. Okay. So the next 3 slides are going to be more about the KK theory, Kaluza-Klein theory. So you want a 5D metric, so you have to add in the extra rows and columns here. And so they define the scalar, G55, and then a vector, B. And the first guess was actually by Kaluza, who thought, well, what if we keep the normal 4D metric here, and then just added these terms here. It turned out that didn't quite work. Wasn't actually a tensor. The determinant was a mess. The inverse was a mess. And so it was actually Klein separately who figured out that adding in this extra term onto the 4D metric that would actually make everything work out beautifully. And so you actually get the determinant is just the scalar times the determinant of the 4D metric, which was very simple and lovely. So continued on, so you're going to assume, like I said, that the fifth dimension is independent. And so if you take any derivative with respect to the fifth dimension, you get 0. And so if you end up doing a coordinate transformation, you end up getting to this vector, ends up transforming just like an electromagnetic potential, which was great since they were trying to unify E and M and gravity. Oh, and that got messed up. That's not supposed to be there. So anyways, the 5D Ricci scalar, so as we've seen in class several times, the Ricci scalar goes as G times delta gamma, et cetera, and then gamma goes as the metric. And so if you just plug the metric that I had on the previous slide into this, follow the same calculations as we've done, you actually get the 5D Ricci scalar is actually the 4D one, and then a term that looks like an electromagnetic field, and then a term that looks like a scalar field. So if you actually just take the scalar field to be 1, or I think there were some that kept it, but I didn't really look into theories where they really kept the scalar. So it looks great. It looks just like the 4D gravity that we see and electromagnetism. So it kind of worked out perfectly.
I'm trying to remember. So there is a square root though, right? There's a square root of -5.
Yeah, that's like the little
so
square root bit.
So
it's
has
like
to be negative or something.
yeah, yeah, to make it work out. Yeah, something like that. So yeah, and then also out of their theory, they said that particles would move in one direction on this fourth spatial dimension. Antiparticles would move in the opposite direction, hence they're distinguished. The radius of the extra dimension is related to the electric charge and mass of the particles. And the periodicity of the fourth dimension would actually give rise to quantization of charge. So all of this sounded wonderful, except when they actually calculated things, they got that the mass of the electron was about 10 to 30 times heavier than it actually is. And so at the time, this collapsed, and nobody thought any more about it until fairly recently. Oh, first, sorry, I have to introduce the towers part of it too. So you get another outcome of having this loop is that you actually get towers of masses. So you theoretically would get an infinite many particles with masses that would be equally spaced out. So if you remember from quantum, you have an ansatz, and if you solve that just based on your boundary conditions, then in this case you would get how the masses are related to each other. So people have done this for not only a circular extra dimension, but maybe a box or a plane, something like that. So they don't always have to be irregularly spaced, like on the previous slide where it was n over r, so the number on the tower over like the radius of the extra dimension. It can be slightly different based on your model. So this is often used to describe a tower of spin 2 gravitons. So the theories I'll introduce next, they kind of talk about this. They have Kaluza-Klein towers of gravitons, and you'd look at the first one. Okay, so this didn't really come back until, so like I said, recently, in 1999, Randall-Sundrum model came about that used the basis of Kaluza-Klein models for their model. So in the Randall-Sundrum model, you have one extra warp dimension, and then you have two fixed points on this warp dimension. One is going to be our brane, where we reside in, that's 3D. The other one is going to be a high energy brane. And so the idea is that by the time gravity gets to our brane over here, it's much weaker than it is actually. At first it was thought that maybe only gravity could propagate between these two branes. It's actually okay for every particle to propagate through as long as it works. And then you can relate, they've calculated out the fundamental masses that we see related to the masses in the gravity brane or the high dimension brane. And then there's also the relation, like I said, between the masses of the KK tower of gravitons. The next one is the large extra dimension model, or the ADD model. I can never remember the last names, but it is off of 3 people's last names. So that was in 1998. So they actually said there could be n extra flat dimensions. There's no, I don't know if there's any limit exactly on the number. I've seen it go up to 6, that's all I know. And they're compactified extra dimensions, so once again, small rolled up inside of some radius. So in this case, only the massless graviton can propagate to these extra dimensions. Unlike the Rendell-Sundrum, other particles could also propagate through. And also, in this model, it's not, you don't quite think of KK towers the same. Because the radius is large, the spectrum actually looks kind of like a continuous spectrum of masses. So it's not quite as, it's not as useful to think about graviton mass states here. And so what you do in this model is to put a limit on the radius of the extra dimensions. So you have, this is the Planck scale, and this would be the scale of new physics. So if you set that scale to the weak scale at 1 TeV, you actually get a series of different sized extra dimensions. So actually, the number of extra dimensions being 1 is actually ruled out because you get a radius that's much too large, and we would have seen it. But everything else is still fair game. The third, string theory, just throwing it in, I don't actually know much about it, but the idea being that string theory, you need many extra dimensions. The only way this could be possible is if you use the same ideas that Kaluza and Klein used, that you have small compactified extra dimensions rolled up. And so that could actually make sense of why we haven't seen all these 10 or 25 or however many extra dimensions they assume. So that is, I think, all I have, and then just some references. I use this lecture a lot, but there's also a good bit in the PDG, the particle data group. They have a nice little essay about extra dimensions that kind of summarizes Kaluza-Klein, ADD, and Rendell-Sundrum models. So that's all.
I sort of missed something about these towers of gravitons. Like, where are the other gravitons, the heavy gravitons? Did you say?
I'm assuming you wouldn't see them. Like, they're so heavy that it would be hard to see.
Meaning they'd be sitting on the other brain?
Yeah, probably they wouldn't quite make it.
Okay.
Weird.
Any other questions?
Is space-time really doomed?
I can't answer that.
Okay, so my talk is going to be about sort of a different version of Einstein's field equations. So the field equations revisited, and we're going to include curvature squared terms in the action for gravity, and you'll see what I mean in a moment. So first, just a review, which we've seen a million times today, of Einstein's equations here, where we have the Einstein tensor, which has the curvature embedded in it. So we have the Ricci tensor, the Ricci scalar, defined. So the Ricci tensor defined, as we know from class, as the contraction of the curvature tensor. Ricci scalar is just the trace of the Ricci tensor. And these guys have the Christoffel symbols inside of them, which the Christoffel symbols finally give us the derivatives of the metric. So all of this is just to remind you that we're only dealing with the second derivatives of the metric inside the field equations. Why did we do that? It's sort of the most natural thing to do. So in Poisson's equation and Newtonian gravity, we always have 2 derivatives. The wave equation is 2 derivatives, Gauss's law. And if you remember from class, once we made this choice, it turned out that the Einstein tensor G mu nu was the only rank 2 tensor, second order in derivatives, that had the vanishing divergence which we needed for conservation of energy and momentum on the right-hand side of the equation. Okay, so in order to proceed with curvature squared gravity, we want to look at the action formulation which we've also seen many times today. So remember, we have the Lagrangian for gravity here, stuck into our Einstein-Hilbert action, and I'm leaving off the matter terms here. I'm just looking at the curvature terms. And then what we do is we vary the action with respect to the inverse metric and set it equal to 0, and then we get the equations of motion, the components of the metric from that. And so, right, so let me go back for 1 second. Right, so we vary the action. By varying the action, we get the Einstein's field equations. And then a good question is, are the field equations sufficient for studying our universe? And by this I mean, is it sufficient that we only consider the second derivatives of the metric inside the Lagrangian? And so one answer is that more precision in our theory is always better. So if the higher order terms give us more precision, then it will be helpful to add them. But is it necessary to add them? And you can think of the higher derivative terms in the Lagrangian as describing like very highly fluctuating space-time, so regions of very strong gravity. So if we have these regions of very strong gravity in the universe, then we might need to go to curvature squared gravity. And so, of course, we have the physical phenomena in which the space-time is fluctuating very strongly is, of course, around black holes, compact objects. And this is just a beautiful picture of the supermassive black hole inside of our galaxy, Sagittarius A star. And very near the singularity of the black hole, we're going to have regions of very small space-time, but with very strong gravity. And this is just quantum gravity, like Michael was talking about. So in the quantum gravity regime, so are Einstein's field equations sufficient for, whoops, sorry. You guys, next one, sorry. So in the quantum gravity regime, is the curvature squared gravity actually a decent theory that would describe quantum gravity? And it turns out that Einstein's gravity is not perturbatively renormalizable in 4D. This is directly from Professor Hamber's textbook on quantum gravity. But he says that it can be proven that higher derivative gravity is perturbatively renormalizable. But unfortunately, other problems are introduced into the theory, like it's not necessarily unitary. And from what I could understand from reading his book, it's not an appropriate theory at this time of quantum gravity. So, but it could be useful for cosmology, so on larger scales, especially depending on how you feel about the Big Bang. Okay, so now defining curvature squared gravity. So all you do is you take the Einstein-Hilbert action and you add in the curvature squared term. The way I'm going to do it here is the simplest way, which is just adding in the Ricci scalar squared. But of course, there's various ways that you could add in curvature squared. You could have the Ricci tensor squared, full curvature, the Riemann tensor squared, or the Weil tensor squared. This is just the trace-free part of the curvature tensor. And it also turns out that the only two independent curvature squared terms are the Ricci scalar squared and the Ricci tensor squared. So, okay, so we do the same thing. We vary the curvature, vary the action, the new action, and see what kind of field equations we get from varying the action. And if I did the calculation right, it looks like that the new field equations are Einstein's field equations modified by twice the Ricci scalar term and a Ricci scalar squared term. Does that look correct to you?
More or less.
More or less, okay. So, so this is how our gravitational equations, field equations are modified, I hope. And then, and so the next sort of obvious question, I think, is that how is cosmology affected by these new gravitational field equations? And just to remind you what our universe, our isotropic homogeneous universe, what the metric in our universe is supposed to look like, it's the FRW metric here, where the R of t is the scale factor, typically called A of t in the literature. So once we substitute this metric into Einstein's field equations, we recover, or not recover, but we actually obtain the behavior of the scale factor, A of t. So now what we want to do is put this metric into the new field equations and check the behavior of the scale factor and see if it gives us the same universe that we have with Einstein's field equations. And so the thing I won't change is I won't change the fact that we have our stress energy tensor for a perfect fluid in our universe. So the right-hand side is going to stay the same. And these are the old equations of motion for the scale factor in Einstein's gravity. And just a reminder also that in the radiation-dominated universe, solving for A of t goes as t to the 1/2. In the matter-dominated phase of the universe, it goes as t to the 2/3. And also it turns out that at t equals 0, if you put the scale factor back into the curvature, the curvature blows up, right? So this is our Big Bang. And so the conclusion is that once you put that metric back into the new field equations and you solve it for the scale factor, I think that the initial Big Bang is actually smoothed out. It doesn't exist anymore. Again, if my understanding is correct. And I think that this is very much like inflation, Mo, that you're going to talk about. That there's no Big Bang in inflation also. Is that correct?
There is.
There is.
Yeah, inflation's kind of separate from if there's a Big Bang or not.
OK, so that's weird. The paper that I read said this. So apparently one type of inflation can smooth out the Big Bang, but certainly other ones that Mo's going to talk about do not do that. Tell me.
There's no unique notion of inflation. It depends what the inflation potential you use. So you can have different scenarios.
Okay.
To some extent, that's also true of higher derivatives theories because you can have more than one curvature square term, right? You look
That's
at
true.
only, yeah, so.
But there's only one more curvature square term that we could put. OK, but that could affect it.
Yeah, well, the equations get very complicated when you have both.
Okay.
They're actually quite long, right?
I saw because you have it in your book. OK, so there may or may not be a Big Bang in the new field equations. Did you have a question? Oh, OK. And actually, and that was the anticlimactic conclusion. So which set of equations actually describes our universe, and was there a Big Bang or not? And this, of course, is to be continued. It's one of the unanswered questions for our universe.
Yes.
Then that's it. Thank you very much.
Very good. Thank you.
Any questions before I go away? Aaron, tell me.
Yes.
Andrew, yes.
Did you solve for like AFT, or is the inflation then?
I have the calculation here. I don't
Like how different
trust
is
it.
for matter one? What did you find?
I don't know. The thing that I solved for was the new field equations. That I can tell you definitely. What A of t is, I got 2 different answers when I did it 2 different ways, and I don't trust my calculations. And not only that, but the very strange thing for me is no matter how many Google searches I did, I cannot find A of t that somebody else did so I could check my answer. Don't you think that's weird? Anyway, so the answer is I don't know the form of A of t.
It's a work in progress.
It's a work in progress. Thank you. Aaron, tell me.
Yes. As based on what I've come across with, so including the higher order curvatures in gravity. So have you come across the term Gauss-Bonnet gravity?
Yes, I did.
Yeah, so it's like the variation of that leads just to a trivial boundary term.
Mm.
But did you ever see any info on quantum effects there, fluctuations? Does that contribute?
Aaron, not that I know of. In my understanding, I read 2 papers on Gauss-Bonnet theorem yesterday. I thought that was in 5D, but I must be wrong. Professor Hamburg?
Well, the boundary is where, it's some faraway galaxy at the end of the universe, right? That's not going to affect things locally.
Yeah, but I mean that's why when you take the
from a
variations,
from a Gauss-Bonnet
or the
theory,
whole
you will not
variations.
get you will not get a modification of field equations, will you? Right?
well,
Locally.
just
That's right, because
possibly,
that's the variation of the action.
because when you consider, so classically you said the duration equals 0, but quantum mechanically,
The most interesting forms are the ones that are not Gauss-Bonnet type. Right? There's actually 2 of them. There's 2 topological invariants. One's the Gauss-Bonnet one, the other one is called the Hertzsprung signature. So those are not particularly interesting. It's the ones that actually modify locally the field equations that are the most interesting ones, both for the classical and for the quantum aspects, I think, at this point.
Because all the physics happens in the bulk. Is that what you're saying? Yes.
Did you?
Tell me.
Is there a radius of the horizon or black hole different than the Schwarzschild?
In the Schwarzschild, that's a good question. I did not look at the Schwarzschild metric. That's a very good question. Put that back into the new field equations and check it out.
Yeah,
Same for the Kerr metric.
It's being done. I just don't remember exactly how it changes.
I say that some type of big bound similarity can be avoided in modified theory.
Yes.
So what about the gravitational collapse at the end of the star?
Yes, singularities are affected by short distance modifications to gravity.
Yes.
This modifies gravity at short distances, right? So singularities usually also do short distance behavior, and so they are very much affected by this. So that should keep you and your mathematicians friend busy for quite a while.
Thank
Well,
you.
I think it was excellent. I think we should move on.
Thank you.
Okay, for those of you who don't know me, my name is Aaron Sofa, and I'm going to talk about the Dirac equation in curved spacetime. So there's a common popular science sort of myth out there, general relativity and quantum mechanics don't really talk to one another. That's true if you interpret it the correct way. So what I'm going to do is still treat gravity classically. The only problem comes when you try to quantize gravity, which is what the next talk's going to be on. So for this talk, gravity is just our regular general relativity, and we're just going to see what complications arise when we jump to curved space-time. So what is the Dirac equation? That's kind of the place I wanted to start. So when you took your first quantum mechanics class, one of the first equations you'd have come across is the Schrodinger equation. But that was treating everything non-relativistically. So you had an equation that was E equals p squared over 2m, the classical relation. You canonically quantized, and in the position basis, that turns into your Schrodinger equation. So this is all for a free particle, not complicating things by adding interaction terms. So I want to generalize this to include relativistic particles. And so it turns out a whole spew of weird things start happening when you do that. So I know a lot of you have already come across the Dirac equation, especially those of you who've taken a year of particle physics and quantum field theory. Just to make sure everyone's on the same page, I just wanted to quickly give a brief lightning overview of that. So this is what I just went over with the Schrodinger equation. Let's try to do the same thing for the relativistic case. So my slide will advance. So relativistically, instead of E equals p squared over 2m, we have the magnitude of the form momentum is equal to m. Throughout this talk, I'm going to use relativistic units, so there'd be factors of c that are all over the place here, so not including those. So you use that, and then replace your energy with the Hamiltonian operator, momentum with the momentum operator, and you end up with an equation that looks like this. That's called the Klein-Gordon equation, and actually that's the equation Schrodinger came up with before the equation that's named after him now. So he came up with this first, so why isn't this called the Schrodinger equation? Well, it didn't predict the energy levels of hydrogen correctly. So what's the problem there? Well, the Klein-Gordon equation that you just saw it treats bosons really well, so particles of integer spin. Fermions, it doesn't quite give the whole story, so that's why it didn't predict the energy levels correctly. You can go through a lot of work, which you would do in the third quarter quantum mechanics class here, for those of you who have taken it or are currently in it. And you would end up getting this. So this is the Dirac equation. And you'll sort of notice, so on this side I have m, IH bar, and then this new stuff here. The way to think of it is it's sort of like a factored version of what you just saw here with the Klein-Gordon. So it's like you're taking, well, square root on this side because both factors are equal to m, but it's not really a square root, it's more of a factor. But picture factoring this box operator with the h bar squared. So that's just where that comes from. This is all special relativity, no general relativity yet. So now we want to look at this in curved space-time. So, well, what's the usual recipe for that? Basically looks like this. You have tensor, for any tensor quantities you have, you take your Lorentzian indices. So I'm going to use as a convention alphas and betas will mean your normal special, in the special relativity like case, in other words, flat space-time. And then the mu's and nu's will be your curved space-time. So these are the general curved space-times. So derivatives become covariant derivatives. Your flat metric becomes your curved metric. Okay, so let's take that recipe and apply it to this right here. So, okay, well, this maybe looks like, a tensor here and a derivative there. So maybe we just want to kind of do this. So that may look promising if you haven't looked at this before. But I skipped over a part when I brought up the Dirac equation. These objects here are no longer just a wave function, the same case it was for the Schrodinger equation. In order to factor the Klein-Gordon equation you saw on the previous slide, you basically need to define multi-dimensional spinors, quote unquote. So what basically happens is you get spin and antiparticles sort of for free because that's the only thing that makes this work. The downside is when you do this, this is not valid. So why not? Because these spinors they have degrees of freedom that are beyond your normal space-time indices. It has its own spin space. To put that very mathematically, you talk about group representation theory and how you can't represent them. Basically, spinors do not transform as tensors. A spinor is not a tensor. So just doing this by itself, that is not going to work.
Eric, can I ask you a question?
Yeah.
But it doesn't look like we have a tensor on either side of that equation. Is that true? So it could still be equal?
Well, so the spinors here, we're going to have a problem. So a spinor, when you rotate it, say do a spatial rotation by 2 pi, you pick up a minus sign. That is, any other tensor, you're back to the same spot. It would have to be equal. So it's really these spinors. So the spinors here are these size, and these gamma matrices. So this is a matrix here, this gamma. It's not just not just a component like you'd usually see.
That makes sense, but don't we pick up a minus sign on the right-hand side and on the left-hand side?
Well, so you have this covariant derivative, right? So you're going to get things that just don't match. Okay. It just, Weinberg said no. Okay. I think I just don't want to spend too much time on it. Yeah, I could probably come up with a crazy example where you go through it and actually prove that it doesn't work. Yeah, I'm just going to take that for granted. And I'll point you to Weinberg.
Another issue is that the gamma mu is not a 4 vector because it's just a matrix. So, right, the gamma mu is just a matrix and it has a very special form that we broke down in the other class, right, in 215C. So that's not supposed to transform the general coordinate transformation.
Yeah. Okay, so that attempt kind of failed. So what are we going to do? What are we going to do about that? I mean, we still want to study the Dirac equation and curved space-time, or do the best we can. So I say these things called tetrads are to the rescue. So what is a tetrad? How is that going to save us? Well, let's back up a step and just ignore the tetrad part for now. We'll get back to that in a second. For now, I'm just going to define a new set of coordinates, these etas here. Just like your x's, except these are going to be a special set of coordinates. These particular coordinates are going to be locally inertial. So the principle of equivalence says you are allowed to do that. In the neighborhood of any point in space-time, you can choose locally inertial coordinates. So what's the idea? So here's some patch of space-time. And our normal coordinates, I'm just going to call them x. So those are your x mu coordinates. They map to x space, and I'm just going to draw the first two. So x0 and x1. So they match to some neighborhood of this space here maps to that. And I'm saying these etas are just like regular coordinates. So I'm just going to map to a different coordinate system. And so eta 0. So I apologize, but this wasn't my doing. Eta is also the notation for the flat metric, not the same thing. So now we have some patch in eta space. Okay, so these etas are locally inertial. So what differentiates these etas, eta coordinates, from your general x coordinates? Well, by being locally inertial, it basically means they obey when you feed vectors in this basis into the metric, it's basically your 1, minus 1, minus 1, minus 1 metric.
These are what we call the psi in class. He calls them psi, he calls them eta.
Yeah, so Weinberg, yeah, they're like different notations. It seems to be no common agreement. But yeah, they were mentioned. Okay, so let's take a look at vectors and covectors. So how do I write a vector in the eta space if I know its components in the x space? Well, the transformation rule for a vector is this here. So I'm literally just transforming from one coordinate system to another. And so here's where these tetrads come into play. That's what these E alpha mu's are. So right now, there's absolutely nothing special about these tetrads. They're just relating one coordinate system to another, with the stipulation that the alphas, remember I said I was using alpha for flat space, the alphas are the eta components. So I'm saying eta alpha those are these. And then a similar transformation law for covectors. Let's get that. So basically I'm introducing some fancy terminology for just a normal coordinate transformation. So far you haven't really seen how this is going to be useful. So just briefly, a couple of key properties that you get out of these. So again, remember these e's here are just partial derivatives. This is just your normal partial derivative relations. So just keep those in the back of your mind. Just food for thought for now. But the etas, eta coordinates are special, so with the alphas and betas. If I transform from one set to another, it is just going to be, since flat coordinate system to flat coordinate system, it's just going to be your normal Lorentz transformation, just like in special relativity. So why am I actually doing this? Well, I know how the Dirac equation works in special relativity, and I'm trying to study it in curved space-time. So just use these flat coordinates, and I know sort of how things are going to work. Sounds simple enough, but you have to go through a little bit more work before all this pans out fully. So keep just the normal coordinate transformations in mind, and this here. What I wrote down here is just for a general transformation between flat coordinates. It's going to be some representation of the Lorentz group. It's just basically fancy terminology. What you get out of this is that everything except for those tetrads, you can remember these E things, transform as a scalar once I fix my eta coordinates. So I no longer have things that transform like vectors or spinors. Basically, these components, so Weinberg actually puts a star in front of these psi objects just to emphasize that they are now behaving like scalars as long as I have a particular flat coordinate system in mind. So what does that lead to? Basically, you have two new invariance principles. Both of them should be familiar. So the first one, action must be generally covariant. So it's just your general covariance. Except now, like I said, you're treating all of the fields as scalars. Why? Because I'm moving all of my, say, vector or just general tensor dependence into those tetrads. So yeah, except for the tetrad itself, because that's where that dependence goes to. And then now the principle of equivalence is the other key principle. Can I actually choose the locally inertial frame? That's how I'm invoking that, and it doesn't matter which one I choose. So sort of set you up for a bunch of formalism here. Let's see what we get. I guess I should mention, I kind of said this, you have basically, you don't have scalar tensor spinner, just that's no longer descriptive enough. You have to say, is it a coordinate scalar tensor or is it a Lorentz? So one is describing your general coordinate system and the other is your Lorentz. Does that make sense? I mean, so for the picture, it looks like this. So to complete this picture, my tetrads will transform me from one basis to the other. So depending which direction you go, you'd use the particular, if you're going from etas to x's, you would use this one, and vice versa, going the other direction. So yeah, more on this later. The Lagrangian density must be a scalar, both with both coordinates and in the coordinate and Lorentz sense. So something that some of you may have thought of, well, what about the metric, right? Because gravity, when I'm saying that, how does it behave? Well, I vary the action with respect to the metric. Well, I'm now transforming my g mu nu into an eta alpha beta. So not that eta, now this is the metric eta. Does anyone see a problem with that? Or a potential problem at first glance? Well, if I'm varying the action with respect to the metric, and I've now fixed my my coordinates here, the eta coordinates, so that this metric eta alpha beta, that's now basically just going to be a fixed value. So there is no variation there. So before you panic, basically what you're doing is you're transforming the variation with respect to g mu nu into these etas here. So now you want to think of it as, I'm going to vary my action with respect to the tetrads instead of the g mu nu. So I'm just going to kind of just bring up the formalism as Weinberg.
You can kind of invert that relationship you had a moment ago. You can actually write the metric itself in terms of the e's. And then you can view the e as being basically the square root of the metric.
Yeah, exactly. Yep.
Which I think is a little bit better to visualize what is going on, perhaps.
Sorry.
Yeah, I should put that one on there too, actually, as you can see both.
Yeah. So does it mean just to multiply everything by the inverse metric? And then
No, I think you can just write g mu nu equal to eta alpha beta e mu alpha e mu beta.
Yeah, so if you, basically multiply both sides by the appropriate etas, and then you'll get Kronecker deltas that will just, you'll just get the one that survives.
You can write it up there. You can write it up black or
I don't want to attempt this. I think we'll erase my picture.
you can write g mu x equal
Yeah, so I was suppressing the position dependence. So really this is a function of x. So hopefully no one was confused there. So we want to write this equals what in terms of alphas and betas? Yeah, well I think so first step we're going to want to do, so E mu alpha, E nu beta, and then G eta, it would just be eta, because they're one and the same. That's the clearest way. So now this is fixed, the variation is happening, right, by varying these.
If you look at it this way, if you can read it, then these e's are like the square root of the metric, right? You write the metric as a product of two things, basically. So it's kind of a square root, and because of that, it's kind of convenient when you deal with fermions. Normally, if you don't have fermions, there's no reason to put up with this complexity. Because you actually, as you pointed out, you have two types of indices. You have the coordinate index, the mu's and nu's, and you have the Lorentz indices, which are what he calls alphas and betas, right? So you have those two types of indices, and normally you don't need to do that. You can live with mu's and nu's only.
Yeah, and actually you'll see, I'll show an example of this toward the end. So your normal Lagrangian density, you have your invariant volume element, that's d4x squared g. So where g is the determinant of the metric tensor. Basically, this will become just E, where this is the determinant of the eta.
Exactly.
So it's, in that sense, you can, there it's more apparent that this eta is somehow the square, it's like E equals square root of G. That way it becomes extra apparent that. So spin 1/2. So I talked to Professor Hamber one day after class, and I think it was back in first quarter quantum, about spin 1/2, and yeah, it's hard to get a physical intuition for it. It's not, it doesn't, there's certain analogies you can use, but it's hard to wrap your head around. Somehow it's the square root of the geometry. Leave that up there. So let's go back to, yeah, so the way Weinberg sets this up. So everything basically becomes scalar by doing this, at least as far as the coordinate sense is concerned. So what if your Lagrangian contains derivatives? So basically in that situation, you will need to sort of come up with a new kind of covariant derivative in order, because at the end of the day, the Lagrangian density has to be a scalar in both senses, coordinate and the Lorentz sense. So basically that's what this formalism is doing. You're getting a covariant derivative that will, at the end of the day, make everything just work out. I'm not going to attempt to go through all those steps to derive this, but he puts, to summarize, and kind of describes the process. So that's the general prescription you want to use.
Well, the V is just the E.
Yeah, sorry, I should mention it. Yeah, so in every other reference, it's an E. Yeah, it would be good to know that. So in your mind, replace all of these V's just with E's. So they're just these E's.
What's the sigma?
Yeah, so the sigma is part of the derivation if you actually went through all the steps, which I'm skipping. So let's see, sigma, do I want to do upper or lower? I'll just do lower indices. Sigma alpha beta is going to be, now even this has varying conventions. This will be off by a factor of I depending who you're referencing, but it's basically this, where these are your normal gamma matrices. Let's see. Yeah, it's related to the spin, which makes sense, right? Because by having the spinners, right, that's what brought spin into the picture. Somehow, this covariant derivative should account for that. sort of kind of a wishy-washy explanation, but can't really do much better in 15 minutes. So, title of my talk was the Dirac equation in curved spacetime. So in flat spacetime, that's what it was. So here's now what it looks like in the curved spacetime. So it's sort of the right idea what I kind of put up there before, except now using these tetrads, I can now write it like this. And the problems that I had with the spinors not transforming correctly go away. This now works. Where this D, this big D, is this thing here. Up to a factor of I, depending again who you talk to, but as long as at the end of the day you know, as long as you get those factors consistent, basically you can write the Dirac equation like that. So that's what it looks like. So very, very similar. I guess I'm just going to sort of throw out a few more results. If you're doing quantum field theory and Lagrangian densities, you can also use that in curved spacetime. So this Lagrangian density here is not, so this is containing the factor of E. Normally, depending again who you talk to, again there are different conventions. This may or may not be present, depends if you mean with respect to the coordinates or with respect to the volume measure. But you can write that in terms of the same covariant derivative. Again, make sure you get all of your minus signs and I factors in correctly. And then also in terms of what you get for curvature. This looks very similar to when we just had our regular covariant derivative, except now I have the sigma matrix coming in again. So that's kind of what it looks like. If I were to go through all the details, it would be a couple pages of math. Maybe a half a page for each of these, some more than that. So writing all of this out in terms of all the components and all of its glory, you get that, which looks like a mess. But that's how you can actually get your curvature expressed in terms of the covariant derivative, this omega matrix, which I don't think I formally introduced that. But everything works out. It is consistent.
The omega is like, you should say that the omega is like gamma. It's like the gamma.
Yeah, it's.
Omega terms are like the gamma terms in the definition of the Riemann tensor. So the omega plays the role of the gamma.
Yeah, the idea is it's something like this. This is sort of a somewhat sloppy of a notation because I'm really talking about sort of infinitesimal adjustments to this, but that's the idea of this omega alpha beta. So I'm looking at if you've studied any group theory, this is like in the math methods course, sort of touched on it. But basically, it's your sort of like your tangent space at the identity. So it's like you look at the identity and then just in a neighborhood of your identity map. But that's all mathematical details that I don't care to get into too much. So finally, Einstein's field equations. So what does all this formalism give you? In terms of that, right? Because normally, they look exactly the same, but how do the eta and metric tensor in the eta space and your normal coordinate space play out? Well, basically, your field equations will specify your metric, your G metric, and then you're free to Lorentz transform using your etas. So basically, you can study your Dirac equation in curved spacetime in a very analogous way that you did in your flat spacetime. Your results are basically analogous. You just get some extra. You have to be a little bit more careful, just because now you have sort of looking at flat spacetime locally within a curved spacetime. And I believe that's all I had. So if you want to see more, yeah, this paper here goes into Weinberg does, and this one here both go into these sigmas and omegas and deriving it step by step. So the rest is sort of more general. But yeah, any questions?
Is there any new predictions like there were with the Dirac equation, you know, with the antiparticle and spin and everything?
Well, it's sort of,
Predictions?
yeah, it's sort of the same. Yeah, it's nothing really new per se. As far as, I mean, I'm not an expert in that, but yeah, I mean, based on what I found, it's the same results as before.
Physics.
Yeah, just like you're just looking at a local patch. It's like space, like right. The world is flat. Well, in a small enough space. As long as I stay within a city, I'm not going to notice any curvature. So it's like your fundamental results. You're not seeing any difference there. It's just that now you can look at more of the global structure, at least within the context of treating gravity classically.
Like the fermion predicted from this, does it have any other properties than the electron?
No, like just a general fermion.
Yeah. You know, what the fermion looks in this theory, is it any way different than our typical electron?
Short answer is no.
Now I'm going to be curious to hear what the long answer is.
Well, this gives you the couplings to gravity.
Yeah. I was just looking to see if a dark matter particle could come out of it.
Hmm.
It has to, because that goes there.
Yeah.
So the factor that's counted correctly.
Yeah. But if it's a fermion, it would be a candidate for dark matter.
Because dark matter has to be a fermion?
So we'll leave that for after discussions. So I think we need to move on.
Yeah, maybe for a different day.
So for those of you who don't know me, I'm Michael Gordon, and I'm going to give a short talk on the Feynman rules for gravity. So as Aaron briefly mentioned, well, general relativity, first of all, was conceived within the framework of classical mechanics in a way, and it's currently incompatible with quantum mechanics, which is probabilistic. As Aaron mentioned, there are problems which arise when quantum field theory is applied to gravity due to non-renormalizability. And when gravity is quantized, infinitely many parameters are needed to define the theory. This is in opposition to something like electrodynamics, where you just need, I think, charge, a mass, and you're good. So anyway, just as an example of what non-renormalizability is, since QED is more well known, this is just some funky thing I found online. Funky picture, I don't know, just photons. And anyway, you can turn these into an integral, and roughly speaking, if the power of your momentum in the numerator is greater than the power of the momentum in the denominator, this integral is going to diverge. And one way they deal with that is to have a cutoff called an ultraviolet cutoff if it's an upper cutoff. I believe it's an infrared cutoff if it's a lower cutoff. So I'm going to skip that slide. Anyway, a particle that's predicted in quantum gravity is the graviton. The graviton is massless and it is spin 2. It is massless because gravity is believed to be infinite ranged. The spin 2 comes from GR because, like in the spin 2 comes from the fact that in GR you have that rank 2 tensor to deal with that we talked about in class. And it is hypothesized to be the carrier of the gravitational force. And interactions of the graviton with 2 or more loops are considered non-renormalizable, Anyway, so the Lagrangian for gravity is the Lagrangian for classical electrodynamics with this one modification. So I don't know if you all remember, but your Lagrangian for electrodynamics, you have your kinetic energy part. So, I don't know, you have your kinetic energy part, and then you have your scalar sometimes, and then you have your Q over C J dot A term. Sorry, this is kinetic energy. Okay. So the difference between this and the one for gravity is that J dot A term is replaced by this 1/2 kappa h mu nu T mu nu. And T mu nu is that stress tensor that we talked about in class. H mu nu is another tensor that's related. That's the gravity tensor that we talked about in class. Kappa is a constant. I think it's root 16 pi g when you work it out. Anyway, when all the quadratic terms involving h are considered, I'm sorry. Oh shoot, what did I do? I think I messed this up. There's a manipulation here I didn't quite understand. Huh? Yeah. Anyway. Ooh, what's it wet get for our field equations? We get for our field equations this once you stick the Lagrangian into the action. And the solutions to these equations is given by this. This manipulation is done through a series of gauge transformations. And, well, anyway, you can prove that this is in fact a wave equation. So anyway, the field equations are invariant under a local gauge transformation similar to that for QED. You can have h mu nu prime is equal to h mu nu plus you can perform this gauge transformation, which is similar to the one we did for electrodynamics, which is where you have just, I don't know, a mu prime is equal to a mu plus, what is it, d mu of just some scalar field. The equation is gauge invariant under that transformation. And we can simplify the equation using this gauge transformation to show that the field equations are wave equations. So anyway, we can get diagrams out of this. These are our lowest order diagrams. This is the analog of gravity to Compton scattering. You need all 4 diagrams. The dashed lines are your gravitons, and the solid lines are just massive particles there. Anyway, you can also get high order terms, and you have to introduce these things called Faddeev-Popov ghost particles, and they're necessary due to gauge symmetries. You can get overcounting in your diagrams if you don't include these. Overcount your field configurations because of the gauge symmetry there. You can also get higher order Feynman diagrams like these. Again, the rule is very complicated, so I didn't want to put it on a slide. It would fill up a slide easily. But in these cases, the solid lines are massive particles. The dashed lines that are red there are those are gravitons, and your ghosts are these things in there. So. I also mentioned there are dilatons that come out of that, but that's a bit beyond the talk, so I guess it's kind of the end of my rather short talk there. So anybody have any questions?
Yes, we have a question.
Maybe you already said this, but the h mu nu were the weak field limit throughout the whole.
Oh, yeah, I'm sorry, yes.
So the graviton can interact though with itself. So did that show up in your diagrams?
Yeah, I guess you have this one right there.
Okay. Okay.
I don't know if they can interact with any massive particles, like any and all. I don't think there's restriction there.
That's the last group. That's a macro.
Well, I know it can interact with some, but can it interact with all? Is what she's saying.
Any particle period.
Yes. you're basically taking over the same Lagrange that you have for Einstein's theory, so you don't change that. You just say that now it has to be quantized. So in fact, the Feynman rules, appear to all orders H. You just wrote down the lowest order terms.
Yeah.
And the Lagrangian itself is now polynomial.
Adversary.